Hello again. I'm now going to show you some of the more interesting reactions that have happened during a long run of the spatial string mold simulation. What we've got here are the dominant molecules that were present at round about time step 450,000 in a string mold simulation. And what I've done is worked out the sort of interesting interactions between these that I'm going to go through with you now. So the first one I'm going to show you is a sort of characteristic thing that we've seen in string mold before, but it's nice to see the mechanisms of it, where a replicase molecule has lost the ability to self-copy. So when I press the new reaction button, this graphic now shows you where the bind sites are, and you can see that it's moved from the beginning of the molecule towards the end of the molecule. And most of the code which actually carries out the replicase functionality is now before the bind site, so it's unlikely to be executed unless there's something that we can't read in here that's going on. So I'll just press play and let's see what happens. So the instruction pointer hops through the NOPS and it reaches this closing curly brace, which basically means end the reaction. So we've got here a replicase molecule that is not capable now of making copies of itself when it binds to another instance of itself. And there's some interesting features of that. There's 2 points to make. The first is that for this to exist in any great number, then it must be binding to another molecular species that does bind probably at the beginning of the string somewhere and creates reads this program and creates a copy of itself, and that some of that self-copying might be mutual, although we might be looking at a very long parasite. The second point is that although no new products are made in this reaction, this bound pair will be unavailable for reactions for as long as this reaction is running, and that means that a large conglomeration of this particular molecular species could act as a barrier to other species getting through, because nothing can bind to it while these are running. And although it's quite a short reaction, only 13 time steps, there's nothing to stop these things binding to each other again and again. That might be one way that these molecules have some resistance to parasites. The second reaction that's kind of interesting involves a parasite and species 56713, which is here. Okay, so I'll just delete that reaction and create a new one. Okay, so this is a parasite molecule, but what's interesting is firstly that it's now the active string in the reaction because of the position of its bind site with this particular molecular species. And secondly, this closing angle brace, which has a rather interesting effect on the reaction, which I shall show to you now. Basically, it moves the instruction pointer to the position of the flow pointer, and because the flow pointer is upstream of the closing angle bracket, it means that this reaction is now stuck in an infinite loop. It will carry on forever, or until the decay process removes both of these molecules from the system. So that's kind of interesting because it means this parasite is not able to parasitize this molecular species through 2 steps. Both is all based on the casting this parasite molecule as the active string, and then this curly brace basically means it's locked in it forever. I think it's particularly interesting that this closing angle brace is present in quite a few of the numerous parasite species. There's clearly not an evolutionary advantage in having that, or not one that I've managed to think of anyway. But it does mean that this sequences like this are able to exploit that feature and have some resistance to the proliferation of these species, because although these two are locked into a reaction forever, it means that other instances of this species will not be swamped by this parasite being multiplied by itself. Okay, so let's get rid of that one. Now the next reaction is 53862 and 56713 again. I'll just run this because it's very short. There you go, that's it. So a short reaction, only 6 execution steps. What this does is, again, because it's not binding where the replicase was designed to have its binding site, again it's binding in the functional region of the molecules where the program is. It's only executing a small fragment of the program, and it's actually the part of the program that's responsible for breaking off the copy of the new molecule which would normally appear here. And what it does basically is it chops the active string in half, well, not in half, into two pieces, and it means that this sequence should be present in high numbers in the system, and this created string sequence should also be present in high numbers in the system, but yet they aren't, so there must be something interesting going on there. It might be a way that small parasitic molecules are created as well, although not quite exactly like this. Then the final reaction I want to show you involves 56713, but this time in this position, and 56352, which is this. Let's close that and have a new reaction. Okay, it's important to have those in the right place because the binding site's in the same position on both molecules, and in that situation the simulator will say that string 1 is always the active molecule. So it means that you can, by flipping them around, you can be absolutely sure what reaction you're going to see should this situation arise. So I'll play this reaction, then I'll pause it at a key point. Okay, so play. Okay, so in these last few steps here, starting with this caret and going to here, we see a novel arrangement of the pointers. You'll see that the flow head is in the right place to do the copying, but the read pointer and the write pointer are in drastically different places. In the original replicase, the read pointer should be here and the write pointer should be round about here, so that the read pointer will create copies and the write pointer will write them to this region of the active string, to that new region. What happens is, if I go back a few steps, that this caret operator has lost a modifying code, which is a NOP code, which should be between these two, and that's kind of critical because that modifies the behavior of the carets so that the R becomes the active. The R pointer is toggled to be active on the passive string, but in this instance it's actually the flow pointer which is toggled to be on the passive string. And then when the move operation, which was originally designed to move the write pointer to here on the active molecule, is executed, it moves it to where the flow pointer is via this mutation, and the write pointer goes there. It's just coincidence that the molecule still functions because this operator brings the flow pointer back to the right place for the copy loop to work. And with the read pointer, flow pointer and write pointer in this configuration, what happens is that the active string is copied directly onto the passive string. And you can see that it doesn't really matter how long the passive string is, because we'll just create new slots for opcodes as we go through. Interestingly, the loop escapes in just the same way as the original replicase was designed, but because it moves the flow pointer to here, the cleave operation does nothing, basically, when we get to it, because there's no new molecule to chop off. And you can see that at the end there is no newly created string, and yet the passive string is now an exact copy of the active string. So this introduces a whole bunch of new and interesting dynamics, because it means that in this reaction no empty slots in the arena can be filled. In fact, this reaction can only proliferate through the system where there are existing strings which have this EUW prefix at the beginning that can create a bind like this. So that's completely novel behavior, completely unpredicted, and yet it's existing in the system, and making this 56713 one of the most numerous sequences in the system. Okay, that's it for now. I'll come back with some more interesting reactions as the simulation progresses. Thank you for listening.